All right, let's talk about how AI actually learned to speak our language. We're going to break down the key breakthroughs that led to the incredible tools we're all using today.
So picture this. It's late 2022. A brand new piece of technology hits the scene and it gets to 1 million users. 1 million users in just 5 days. We're talking about ChatGPT, of course. And for most of us, it felt like it just appeared out of thin air, you know? It completely changed the game almost overnight.
But here's the thing, the story of how we got here, all the key breakthroughs that made this possible, that started way before. So how did we do it? How did computers go from being, well, glorified calculators to generating text that feels human? Let's dive in.
Okay, so the first big hurdle was really fundamental. How on earth do you get a computer to understand words? I mean, words are messy, they're abstract. A computer only gets numbers. So how do you turn one into the other?
Well, one of the first clever ideas was something called bag of words. And yeah, it's pretty much exactly what it sounds like. It had some pretty major flaws for sure, but this was a huge first step. For the first time, it gave us a systematic way to turn language into math. First, you tokenize. The computer basically just splits a sentence up into its individual words. We call these tokens. Next up, the system creates a vocabulary. It just goes through all the text it's been given and makes a master list of every single unique word it finds. Think of it like its own personal dictionary.
And finally, the bag of words part. The computer just counts. It looks at a sentence and asks, how many times does each word from my dictionary show up? So every sentence becomes this long list of numbers, a vector. But you can probably already see the problem, right? It totally ignores the meaning of the words and, crucially, the order they're in.
So we needed a better way. And in 2013, we got one. A huge breakthrough called word-to-vec, which finally gave words a sense of meaning by, get this, placing them on a kind of map. This was a massive leap forward. On this map, this vector space, words that meant similar things, like puppy and dog, were now located right next to each other. But this solved one problem and created a brand new one, a really subtle one. Here's the issue. A word like bank would have the exact same coordinates on that map no matter what. Whether you're talking about a river bank or a money bank, the system couldn't tell the difference. It still didn't get context. So for an AI to really get language, it had to learn something we do instinctively, that a word's meaning totally depends on the other words around it. It needed context.
Early models, like something called a recurrent neural network, or RNN, they tried to do this, but they were kind of clumsy about it. They tried to squish the entire meaning of a sentence into a single, fixed-sized package. You can imagine for long sentences, this created a massive bottleneck. A lot of information just got lost.
And then came the solution. It was an idea that first popped up in 2014, and by 2017, it was perfected. It's called the attention mechanism. And honestly, this is the key idea that powers pretty much all modern AI.
Okay, so think of attention like a spotlight. Instead of forcing the model to remember the whole sentence at once, it lets the model focus or pay attention to the most relevant words for whatever it's doing. So if it's translating, you can see here it can directly link llamas in the English sentence to llamas in the French one, no matter where they are. It's brilliant.
This attention idea was so powerful, so efficient, it completely changed everything. It became the engine for a brand new kind of AI architecture, the transformer. And this, right here, is the blueprint for basically every single large language model we use today. GPT, Claude, you name it.
Now, what's really interesting is that this one single architecture, the transformer, almost immediately split off into two different directions. It gave us two distinct flavors of language AI, each built for a totally different job. On one side, you've got representation models, like Google's BERT. Their goal is to understand language, to get what it means. And on the other side, you have generative models, like OpenAI's GPT. Their goal is to create language, to write, to chat, to summarize.
And you can literally see this difference in their design. On the left, in teal, that's BERT. It's an encoder, which means it looks at the whole sentence, forwards and backwards all at once, to build this really deep, rich understanding. But on the right, in pink, that's GPT. It's a decoder. Its job is way simpler in a way. It just has to predict the very next word, and then the next one, and the next one.
So now we have this incredibly powerful framework, the transformer, and the race was on. It was all about building bigger and better models.
And researchers figured something out really fast. With transformers, size mattered a lot. As the models grew, as their number of parameters, which are kind of like the connections in a brain, went from millions to billions, they didn't just get better at grammar. No, they started showing totally new abilities, things they were never explicitly trained to do. And this led to an absolute explosion of innovation.
And that's what brings us to today. This absolute Cambrian explosion of AI models is why we have all these incredibly powerful tools right at our fingertips.
But of course, this incredible speed, this progress, it's also brought up a whole new set of really tough challenges. These models can pick up and even amplify the biases in the massive amounts of text they're trained on. They can also confidently just make stuff up, what we call hallucinations. And because they're so complex, figuring out why they say what they say, well, that's still a huge, huge problem.
When you boil it all down, from simple word counts to this incredibly complex reasoning, the entire journey of language AI has been about building better and better mirrors. They reflect the world of data we've shown them. So the real question we're left with now isn't just about the technology, it's about us. How do we make sure these powerful reflections show the very best of who we are?